This seminar is about high throughput workflow tools, uh, strategies for using them when you happen to have high performance computing available to you instead. And it's kind of an awkward fit sometimes. So we've sort of accumulated tips, patterns, which tools work well, which things about tools work well, all this sort of stuff. And we're going to try and go through that. All right. So the broad plan here. I'm going to start with an introduction and sort of
Oh,
a.
are you sharing your screen?
I am sharing the screen. Is it visible to you?
Oh, I can see it now. Yes.
Uh, because this room has two screens, so it's showing the screen share on the left and it's showing the panel on the right. So I might not necessarily see the same thing as everyone else,
Yep.
but
We're good.
okay. Okay. Um, so we'll do introductions. We'll get sort of a little more detail in the context of high throughput computing versus high performance computing. Uh, and then there is a selection of 3 tools that we're going to go through from the easiest, most accessible, quickest to get running, but uh, missing some features that you might like to have. And then showing the trade-off as you add more feature, if you add more challenge to running it, what features do you gain? What are you buying by putting that extra effort in? So progressively easier to more complicated tools. The first one will be GNU Parallel. The intermediate is a make-like tool called SnakeMake. And then the last tool will be Hypershell, which we are the other panelist is the developer of Hypershell. So you'll get like direct access information about that. Okay. Introduction. So my name is Bill Arndt. I am a staff member at NERSC. I've been here for almost 10 years. Some of that was as a postdoc. I've bounced around doing a bunch of different things. I've optimized bioinformatics codes to run on high performance computing. I worked on an ocean simulator. I spent a few years as a user consultant specializing in helping Joint Genome Institute users. And a couple other things I do. I catalog workflows, trying to find all of them, of which there are at least 492. And I am the organizer of an urgent and interactive high performance computing workshop series that happens at ISC and SC every year. Oh, and dog and cat and baby. That baby is the reason why I can't give this presentation from home. So things will be nice and quiet and stable here. Okay, Jeffrey.
All right. I'll steal the screen for 1 second, then you can steal it back. All right. So I am coming to you from the Rosen Center for Advanced Computing. That's at Purdue University. We are one of the larger campus-based HPC centers, and we're an access resource provider, if you're familiar with Access. We operate a number of HPC systems and provide services to the university and nationally through the Access program. I'm a member of the scientific applications team. And we also have a number of other centers that we operate, such as the Envision Center for visualization and like virtual reality presentation of data and interactive experiences, as well as we have a new center for research software engineering. I am a lead research data scientist, or at least that's what they call me. My academic background is in astrophysics. I got my start in HPC doing computational astro stuff. I've been at the Rosen Center for about 8 years now, doing all manner of things, user support, the application stack, doing software development, research software engineering, consulting, outreach, education, this kind of training. And as Bill mentioned, one of my activities really surrounds throughput computing workflows and tools. of which I am now an author of one for the last 5 years, and I will share more about that later.
Well
All right.
set.
Yep, back
All
to
right.
you.
All right. I've got the baton back. Okay, so sort of the logistics of what we're going to do here. So there is a Git repository, including the training materials, at this address. The link to this is also included in the Q&A document, among some other things. So the ideal situation is someone can go to this repo, clone it, and have access to more of the artifacts than I'm even going to have time to discuss. And a lot of the examples will have detail in that, including things like sort of the running commands, the expected outputs, all of that, like reproduce it yourself where you are kind of information. The design for that stuff, it's hoping to be able to run on a general Linux environment and not necessarily on Perlmutter or another specific HPC machine. But there are some details like Slurm accounts and queues, and maybe if a module load is involved, that won't necessarily be present on the system that you're toying around with, and you might need to make some adjustments to get it to work. Okay, yeah, the question and answer document. There's a tiny URL to that yeah, just as a helpful thing, I'll see if I can get that pasted in the chat. Oh, yeah. And Jeffrey took care of the repo, so that's cool. Okay, we are recording the seminar. The plan is to get it professionally captioned, cut, edited, and it will be made available on the NERSC YouTube channel for everyone's viewing pleasure. I don't think it's monetized, so no like Pizza Hut ads or anything during that. Oh, and there's also a survey link on the question and answer document. I have been told to remind people, please answer the survey beginning, middle, and end. Okay. So what are our assumptions about sort of the user environment and experience for the audience? The assumptions we're making, Linux terminal users, SSH to whatever machine you're using, familiar with sort of basic bash commands, directory structure, that sort of thing. At least competent in getting around the system, not like a Jupyter only user or something like that. You'll have a hard time getting value out of this presentation if that describes you. People who have reason and opportunity to access high performance computing clusters of the size of a couple racks or up to several rows, like large systems. And the expectation is that the way that you access resources on that cluster, it's being shared with other researchers like yourself, and there's some kind of batch allocation system. At NERSC on Perlmutter, it's Slurm, but other places may be using PBS, Torque, Flux. There's 20 other options that are potentially out there. This is another reason that editing example artifacts might be necessary to get things to work. srun gets flipped out for MPI run versus something else. Or your sbatch command is actually a PBS command, that kind of thing. Okay, this slide I have stolen wholesale from Jeffrey because it's perfect for this piece of introduction I want to do. The difference between high performance computing and high throughput computing. High performance computing is expecting small numbers of very large, tightly interconnected processes doing something big and high frequency, simulating a planet, simulating a bunch of particles that are spreading forces all around a very large grid, and the computation for calculating that is spread over entire racks, entire clusters, usually with MPI, that sort of thing. High throughput computing has the same volume of compute potentially, but all of it is independent from each other. It doesn't matter what order it happens. It doesn't need to send messages back and forth using the high-speed network. All of these things can sort of be stuffed wherever they fit, and as long as you get sort of your completion of compute over per unit of time high, then you've got good performance. So when I first wrote this, I used the word conflict, and I guess misalignment is a friendlier way to say it. But there is some misalignment between the expectations of HPC and HTC users and sort of the systems that get procured for these things. The job scheduling infrastructure, the Slurm configuration, the queue structures will tend to be designed to optimize for small numbers of very large MPI jobs, 2,000 nodes at a time, all in one MPI communicator. This infrastructure cannot necessarily handle getting very large numbers of small jobs in a short amount of time. There's databases that have locks that may lock out other users getting access to the scheduler commands. There's databases that can fill up. The record keeping gets bloated and needs to be rotated more often. Yeah. The way that a lot of the high performance computing systems are sort of designed, like the culture that they're coming from, they make those assumptions about small numbers of large jobs. They may choose defaults and design interfaces in a way that something feels like it should be actually solving the problem you want, and it actually doesn't. Like my example here would be job arrays in Slurm. If you have a high throughput job, a job array feels like a very natural solution to that. But unfortunately, under the hood inside Slurm, the job array is being implemented as 10,000 just regular jobs. And those jobs are waiting in the queue like regular jobs too. There's no sort of bulk thing. So for instance, at Nurse, we have a setting in Slurm called Max Job Accrue 2, another instance of something that favors fewer larger jobs instead of many small jobs, where only 2 jobs gain priority in the queue at a time. That prevents someone who submits 10,000 jobs in a minute from locking everyone out of the system because only 2 of those jobs go through at a time. And so we're incentivizing people to try and submit your jobs in a different pattern than that. Yeah. Queue policies, wait times, allocation bonuses. We have policies where we call them capability jobs, but 1,000 nodes or larger get a allocation charge discount because we want to encourage those jobs to get our money's worth for the high-speed network. Yeah, talked about sort of the system defaults. Yeah, and this one is just sort of a joke on the cultural aspect of it. If you imagine like a high performance computing sort of professional, the bearded and kind of grizzled, but well, the kind of person that you'll see at a supercomputing conference, they may look down upon workloads that are not like using the high speed network for what it's for taking time on these machines that can do these amazing giant problems, but using them to do tons and tons of small problems. They might think like, why don't you just do that on the cloud or on your laptop or whatever? But no, this is still valuable computing. And it's also valuable to centers that, if we measure the utilization of our machine, we don't get enough big jobs to fill up the machine. And if we get 80% of the machine filled with a big job, we still need work to use that other 20% for getting the value out of the machine. So we do actually want these jobs. And I push back against that sort of cultural notion. Okay. The summary of the entire strategy for getting high throughput computing running well on high performance computing machines: use workflow management tools to fit your tons of small jobs into fewer, larger applications. Get something that will organize those 10,000 into a call of a manager that is running its own sort of local client that's running the jobs individually, but it all fits in one big job allocation. The different tools that are available to act as that workflow manager have a broad trade-off between how easy they are to use, how much setup, how much configuration, if they even need like extra services outside of the machine, and sort of the power of what kind of workflow you can describe, what features and capabilities you have access to as you're fitting your throughput workload into that one large job. So that's the point where we're sort of trying to organize the progression of this seminar, starting with the easiest, most accessible tool that I know about. It also happens to be my favorite, and I'll spend the most time on it. Sorry, not sorry. Then we'll bring sort of the intermediate tool and tell you explicitly the capability you gain from the intermediate tool is you are able to handle dependencies where some jobs or tasks need to run before others. That's the thing you gain. And the thing you lose by moving from GNU Parallel to SnakeMake is now there's a lot more support infrastructure that's needed on the file system. SnakeMake is tracking everything, the data, the state of the workflow on the file system. So then you have to do more setup of your pipeline. You have to pay attention to sort of directory structure that your pipeline might be using. You may need to think about network file systems synchronizing or caching behavior. That might come up. So this extra bit of overhead is the price you pay for being able to have job dependencies inside your workflow. Another point that I want everyone to come away with is just more like a sort of broadly, even if it's not with these tools, uh, workflow pieces are composable. And most of these tools will be good at one or two capabilities and either non-existent or mediocre at lots of other things. So if you are willing to put in a bit of brain power to sort of organize your roles for the different phases or structure or tree structure or division of labor, you can choose the tools that hit their strengths on each one of those roles and end up with a much better design in the end.